Hi, my name is Anthony Pagan. This is a presentation of my final paper on analyzing historical server performance metrics to predict critical system errors before system degradation. So many organizations rely on monitoring systems to monitor performance of their back-end systems. And the expectation is that the monitoring will notify support staff when critical systems are in a critical state. Unfortunately, many times support teams are only alerted after a system is degraded, and in some cases, manual monitoring tuning results in false alerts. So the main goal of this project is to build a proactive monitoring model based on performance metrics that can be correlated to system events and allow teams to build automated resolutions. Such a system would reduce support costs and increase efficiency while minimizing false, non-actionable alerts. So there are several journals with different approaches to proactive monitoring that include some self-healing mechanisms to system performance issues. Some methods include the well-known algorithms, and in some attempt to build their own. So one approach is LSTM, which is a combination of long and short-term memory using RNN. An RNN, or recurrent neural network based on LSTM, is called an LSTM neural network. And the subtle difference of LSTM versus KNN is that it uses a forget gate in addition to the input and output gate in RNN. This gives a model additional strength when using sequential data. So LSTM can use autoencoder to capture the temporary data from a monitoring dataset. It can then use a deep neural network to determine each metric rate. LSTM can also be used as a one-to-one or many-to-one neural networks, where it attempts to predict the performance metrics to find relationships between the dependent and independent variables. So the Monte Carlo approach uses a long-term non-stationary data and uses a residual short-term release process to capture a random application revolutions with time. The short-term data is modeled as a traditional auto-regression process. In this approach, the parameter for long-term and short-term data are estimated using the sequential Monte Carlo, which is SMC. And this approach is similar to the time series prediction framework for resource usage prediction analysis. It uses a different method for selection of relative subset of data and a stability-based joint framework for selection of a suitable feature selection. So the other options are decision trees, k-means, Gaussian clustering transformed with PCA. In these approaches, each metric is scaled to 0 and a unit of variance. Then principal component analysis, PCA, is used to transform the metric to get the top dimensions. Now, because of the type of data sets, our objectives, our approach is similar to Monte Carlo method described. Because we have time series data and are trying to predict a binary variable where 1 would equal ticket and 0 would equal no ticket. To impute any missing data, we're going to be using a time series data. And for this paper, we will compare several models, some linear and some non-linear models. So we'll use linear regression, which is used for explaining the relationship between a single dependent variable versus one or more independent variables. And ridge regression uses a synchrous technique that tries to minimize RSS. It uses delta tuning parameters as a shrinkage penalty. Lasso is similar to ridge, but it fixes some shortfalls of ridge by using a penalty to get to an absolute value of beta to allow the variable to be exactly 0, which also allows Lasso to perform variable selection. Some of the nonlinear approaches for this paper are decision trees, which take the shape of a graph that illustrates possible outcomes of different decisions based on a variety of parameters. And lastly, SVM, which aims to minimize the effects of outliers with an approach that uses a subset of training data points called support vectors to predict new values. In this paper, we will compare the top performing model to Keras neural network to derive our final model. Now, neural networks attempt to predict the closest sample in the training set space by taking the mean of their response values, where k represents the number of closest samples to consider. In addition, we will be using Box-Cox and LDA to finalize our independent variables. And lastly, for the time series data, we will use the NA-Kalman function, which will be used to impute the NA values that are derived as a result of transformations. So our data set is based on two files with performance metrics of several development servers. Both data sets are related by timestamp and managed entity ID. One data set includes the severity of the alert, which helps determine if an alert would generate a ticket to support groups, while the other data set includes the performance metrics. Combining the two data sets allow us to know the value of each performance metric when an actionable critical alert results in a ticket. The initial data has several categorical columns that describe the object, the alert, the priority, the severity, and more importantly, the sample value. We add a recognizable server name and a ticket column. Once we transform the data set, we are left with some of the original categorical columns, and we place the distinct samples of values into their own columns. Some of the metrics are related to CPU, disk, and memory pages. In the initial visualization, we show that there are multiple ops master columns that are highly correlated. So any highly correlated independent variables columns we should remove, since they provide no additional value. So we transform the data by removing any categorical value columns that give the same details. So we remove the alert description, the object name columns, and spread by the sample value. So as stated before, we created a ticket column where severity 2 transformed to 1 for tickets, and any of the other values are given a 0 for no ticket. And we also generate a server column for a more readable entity name. The spread of the data causes a large amount of NA values, so we use the NA-Kalman function to impute the data in the NA rows in the time series data. Lastly, since all of the ops master columns are highly correlated and have similar values, we combine all ops master columns to one master average column with its row means value. We see after the transformations, we can still see columns with NA values. As a matter of fact, the remaining columns with NA values have greater than 90% of their values missing, which is not useful for our model. Therefore, we remove any remaining columns with missing data. Although our final data set has only 12 out of the original 21 columns, the feature plot shows that 6 out of the 12 are in fact numerical. The BIC plot tells us we can very likely use 3 out of the 6 remaining numerical columns for predictions, and the find correlation function lists the 3 for removal as log file drive space, database size, and database drive free space. Similarly, the GLM function and the BIC agree that % processor time, database drive free space, and page per second are relevant. So we begin the modeling by testing the general linear model. The results show that there is no difference when comparing all numerical models to ticket using GLM or the reduced column based on the step GLM model. This tells us additional columns can be eliminated as some columns are still highly correlated and would provide similar statistical results. We use the box-cox function to determine some possible lambda values to transform dependent and independent variables. The box-cox function results gives us 2 as the number of x independent variables that should be required for any models. The vector under the plot has the lambda for x independent variables. In model testing, we use 5 models, and the 5 models that we discussed earlier for comparison, and select the best model for the dataset to compare to the Keras neural network. Each model test includes a box-cox parameter as a pre-processing option. We split the training and testing set by 70 and 30%. We use RMSE, R-squared, MAE, AUC, accuracy, TPR, and FPR to select the best model of the 5. And we're using the box-cox pre-proc options to integrate the box-cox derived lambda into all of the models. Since a higher R-square and a lower RMSE MAE point to a better model, we select the C-tree or the decision tree as the best model based on these metrics, while the linear and the ridge regressions are tied for second. Based on the above metrics, we will compare C-tree or the decision tree to the Keras neural network. Below are the top variables for linear regression. We can see that percent processor time, database dry space, and the master average variables are important. For comparison, we also plot a tree diagram which gave us similar results with the top 3 predictors, which are also selected in the top 3 nodes of the tree. The Keras implementation show an accuracy and MAE MSE decreases at a higher rate than the C-tree. And the Keras implementation also has a higher accuracy and is therefore the more accurate and the preferred model. Part of the modeling objective of this paper is to predict the ticket generation and provide a possible resolution. We update the data set to include some randomly sampled ad hoc resolution text. In a real world scenario, the separate database and application would be used and merged with predictions. To simulate, we select data from the original data set based on the indexed rows from the trained data set and merge it with the predicted data set from Keras model. We then generate a random resolution vector based on random text and select each text based on a random sample probability and then merge that data set with the original merged data. We further subset the data to select only rows where predictions and the actual equals to 1. We group by alert name, count by resolution, and order by resolution count descending. We further mutate by adding sample hypothetical code for automated resolutions. The final data set takes the top 2 resolutions for each alert and can be used by a support team to resolve issues either manually step by step or to build automatic scripts for automated resolutions. These scripts can be integrated into any monitoring system to take proactive actions based on targeted metrics to resolve issues. In conclusion, we have taken some performance data from several development machines to attempt to predict degradations of systems to proactively initiate resolutions. During our data analysis, we narrowed down the number of variables. We looked at several models which resulted in selecting the decision tree and Keras neural network. In the end, Keras neural network showed better performance. In addition, we merged our predicted result dataset with a simulated resolution dataset as a way to initiate automated resolutions. Although we experienced high performance with carriers, we tested with a small sample of servers. In addition, these servers were development servers, which would not have the same load as a production server. Further testing should be done with higher amount of production server data, in addition to expanding the other classes to other classes of data. From the review of the data, these servers are very likely a mix of databases and Active Directory servers. So it would be good to see how these models and other models would perform on a mixed class of production servers with heavy load. Thank you for viewing this presentation.